I'm Michel Bachmann from Athens, UGA, from the Center for Simulation of Physics. And he will talk to us about the generic structural transition in macromolecular system. Please, Michel.
Okay, Bismarck, thank you very much for the nice introduction. I would like to thank first, of course, all the senior and junior organizers of that beautiful workshop, and happy birthday, right? 20 years. It's a good tradition, and I'm so happy to be part of it nowadays. This is my third workshop in a row that I attend, or I'm allowed to attend, and it's always nice to get back to Brazil here. Yeah, so part of the work that I present here was done in collaboration with colleagues at the Federal University at Mato Grosso in Cuiabá, and also Federal University in Minas Gerais, Belo Horizonte. So it's about generic structural transitions in macromolecular systems. Generic is everything that is not specific, so we really try to get access to information about these kind of polymer-like systems that are hopefully applicable to entire classes of polymer systems and not very specific to certain individual ones. Of course, they should also, certain specific properties of these results you should, of course, apply also to individual systems. Okay, so let me just go through the overview briefly after a short introduction that contains some slides that I have already presented in Florianopolis. But here, instead of going into any detail, they just serve as kind of leading you into the field and then, of course, extending the talk into the new material that has been worked out in the last few years after that last conference. Okay, so I will be talking about coarse-grained modeling simulation, as I said, by making use of some examples that I have already discussed in the past. And the last three topics here will be the new stuff: stabilization of helical structures, the adsorption of helical polymers to solid substrates, and of course also the adsorption of flexible polymers by using very simple models. Okay, just as I said, a kind of an introduction into why all this is necessary. There is much more to it than I can present here. We have had the discussion about what is a phase, what is phase transition, do we understand phase transition? We had all this in the past few days already. I would add to all that that I don't really care anymore about what is the definition of a phase or phase transition, because we have to deal nowadays statistically, thermodynamically with systems that are of finite size, but undergo such substantial changes, structural changes, that I think, should start to learn whether they fit, these changes fit into this context of phase transitions. So generalize the idea of what a phase transition is actually. So your biomacromolecules, most prominently, for example, proteins, are represented by a geometric structure in the living organism, like a cell, for example, and this geometric structure, which has its origin in the genetic code, finally fulfills a biological function. So there is an interconnection between these three major fields here, basically fields of research, but we keep in mind just that structure is important for function. So I want to learn something about the structure because the function sensitively depends on the correct structure that the protein folds into. We have that understanding in thermodynamics and statistical physics that there is something like a free energy landscape, so reasonable parameterization of this free energy landscape. We should be able to locate the global minima and then maybe able to associate that global minimum of the free energy landscape with parameters or certain special values of parameters that represent in some generalized way the structure of the dominant structure of this object that we're interested in. Okay, so here's such a sketch. So we have some kind of free energy landscape. It certainly has a lot of local minima as well, because as I said, these objects are relatively complex. We expect that in this global minimum here resides the structure that we are interested in, or that represents the functional structure. The problem is, still to date, I think we don't really have a good clue on what we should put here on that axis. So how to parameterize the free energy landscape? Of course, physicists statistical physicists like to introduce something like an order parameter, because maybe we see some connection to phases and phase transitions, so order parameters. Chemists, of course, use something like reaction coordinates. people who are specialized on, for example, spin glasses or glassy systems in general would introduce something like an overlap parameter. So all this is reasonable in some sense, but in contrast to, for example, to parameterizing the free energy landscape of an Ising model, where apparently the magnetization is a good order parameter that helps me a lot to understand where and under which conditions the paramagnetic phase transition happens. Here we have nothing that seems to be really of general value at all. So you can find representations, but it seems to be very specific. So this entire picture is something that I also start disliking more and more, although I will exclusively use it in this talk. We are working on different methodologies momentarily, but I will keep this traditional approach for this talk, or what I present in this talk. Okay, so let's talk a little bit about these proteins as kind of the major class of biologically relevant molecules that are of interest and are extremely complex in their structure, and we want to understand how these objects, for example, fold into this functional structure. So protein consists of many atoms. Typical sizes of proteins are or contain 10,000, 100,000 of atoms. So they are not really small anymore, so forget about quantum mechanics or quantum chemistry. They're not really large, so forget about macroscopic theories. They are somewhere in between on mesoscopic scales. That's the first problem that we have to figure here. Proteins fold spontaneously, typically, in most cases, into this so-called native or functional structure. That means they know what to do. So when we want to simulate these systems, we have to learn what we have to do, but these natural objects know by themselves basically what to do. So it's possible, it's realistic. Again, we suspect that there might be some free energy-driven stochastic process behind that folding pathway. The time scales on which this folding process happens are surprisingly short, given the complexity of the problem. They are a nightmare for people doing molecular dynamics simulations, of course. So that's the next problem, how to simulate these systems, which kinds of algorithms do you have to use. What I want to specifically target today in this talk here is what are certain constraints, restraints, properties of all these systems, and how can we model these in a simple way, and to what or to which results will that lead to? And the protein, again, is kind of a prototype example of what is relevant here. As I said, such a protein is not a flexible object at all. It has or consists of, as I said, 10,000, 100,000 of atoms, but not each position of an atom is let's say, three-dimensional degree of freedom. As I said, there is no real flexibility in the system at all. So what are the degrees of freedom? Well, we have these torsion angles, so we can rotate entire groups, chemical groups in the system here about certain bonds. Not all of them are relevant, but you see here I've indicated some of those represented by the entire vector of angles, torsion angles that are relevant. These are real degrees of freedom, and in most cases you have really the entire space available for all of those with few exceptions. What is very interesting on the other hand is, I think someone presented in a talk or said in a talk yesterday, or talked about protein, or mentioned proteins and mentioned bond lengths and bond angles as kind of the degrees of freedom. They are not. They are not. I mean, bond lengths are strictly rigid here for these, or in these systems under physiological, under functional conditions, if you like, and almost the same applies also to bond angles. So the angles between bonds are, I mean, hardly fluctuate under these conditions, and as I said, the bond lengths themselves are basically constant. So nature has decided that complexity is best dealt with to achieve the goal of folding such a complex system into a functional structure. Nature has decided that the best compromise is to have only a limited or relatively small number of degrees of freedom, but a large number of restraints and constraints. So now you can think about that in terms of simulations. Is that an advantage? Is that a disadvantage for the simulation? Well, I cannot answer that question at this point at all. Anyway, that's just, as I said, the background why we are interested in these systems. Let's just formulate some of the consequences of all that. So proteins themselves are heterogeneous molecules. So these building blocks are, proteins are linear chains of certain building blocks called amino acids, and we have different types of amino acids, so it's a heterogeneous chain. So you have some sort of intrinsic disorder in the system right from the beginning. I will not apply or will not make use of that fact in the applications today anyway, so I don't go into this detail, but that can, you know what happens if you have intrinsic disorder that can lead to frustration, can lead to glassy effects, stuff like that. I neglect that part completely today. Important is that these systems are finite. It does not make any sense to make them larger. As I said, their origin, the intrinsic properties of a protein are encoded in the DNA. All this is finite. Typical system sizes are 10 to maybe 1,000 nanometers. That is neither very small nor very large. So we are somewhere in between. And from that point of view, we call that a mesoscopic scale. As I said already, geometric structure is correlated with the biological function. That is important to know. So that's a real thing that works. So we have to understand why that can happen at all. So what is the structure formation process? What does it have to do maybe with something like phase transitions on finite scales? So what can we say? Does that make sense? Doesn't that make sense at all? Do we have something completely new that we have never dealt with before? Questions like these. We have no thermodynamic limit available. So forget that. So throw away all these definitions that we are used to. Throw away all these theorems. All the theorems are formulated under this condition. We are in the thermodynamic limit. No, it's not existing here. That means most cases we are not really able to formulate something like scaling laws. In many cases, it just doesn't make sense to ask that question. But that also means that depending on what quantity you measure in experiment, in simulation, you will hardly find consistency. So you will have to ask another question: what is the transition point? Where does it happen at all? So finite size effects, surface effects, these systems are finite. That means they have a surface. I have not yet mentioned that they are embedded into a complex environment. And even if it's only water, that is complex enough because we don't even understand water very well. So the entire structure formation process happens in a solvent that can never be ignored. So surface effects matter in most cases, or in many cases. The surface of such a molecule is much more important than what is embedded in the bulk. So this is what one has to understand as well. And as I said, because of the heterogeneity, we have to deal with disorder effects as well. Here, just see a few examples of prominent examples of proteins or structures composed of proteins. And you see here the orders of magnitude of atoms that we have to deal with. All these are fascinating objects in their own right. But as I said, I don't want to go into any specifics here. That's definitely not what I want to do. I want to keep things very simple. So let's formulate the task. We want to find the simplest possible models, so-called coarse-grained models. We have no real clue to how to perform a systematic coarse-graining process. So we just start basically from some phenomenological approach. We replace each of those chemical groups which are connected to each other by chemical bonds. We replace them basically by something we call a bead or a monomer, which has a certain volume, for example, it's an exclusion volume, which accommodates all the atoms. So that's the first incredible simplification that we do here. And then, of course, we introduce something like bonds. And as you have seen in the protein case, of course, we have many of those bonds. But I want to make that object here, for example, one of those blobs. And here maybe we have another one. And you see there are several bonds in between. And we introduce something just like an effective bond here. So this is what is shown here. So what do we use? We use a bond potential. In some cases, in many cases, not really the essential part at all. It just makes our simulation life somewhat easier if we introduce that kind of sort of degree of freedom, although I told you that for proteins, it might not make any sense. So let's forget the proteins. This was just kind of our motivation for this approach, and let's completely focus on homopolymers. So all the beads here have the same physical-chemical properties. The bonds are all the same between these beads here. We only have a linear chain. As I said, we have a bonded potential, which is a first approximation of harmonic potential plus some anharmonic terms in a sense, and that's why it is often conveniently written in this form. There have been other forms of this potential introduced in the past, for example, by Kremer and Grest. Here we use the form that was used by Butter, Sharia, Binder, and co-workers. For the non-bonded potential, or for the non-bonded interaction, we just make use of the fact that if these monomers come relatively close to each other, or within a certain distance, they will feel polarization effects inside them, which leads to kind of van der Waals forces that we model by ordinary Lennard-Jones potentials. Essential in all these cases here is that we have a relevant length scale, here the bond length, for example, or some optimal bond length, and an energy scale. So a length scale, energy scale, associated to each or assigned to each of those potentials. Same, of course, with the Lennard-Jones potential. We also have an optimum distance here and appropriate energy scale. These are parameters. I mean, I try to build a model, but I want to keep the number of parameters as small as possible. That's what we call a generic model. Reduce the number of parameters. These protein, if you really want to model a protein with all degrees of freedom, then you deal with effective models that contain hundreds to thousands of parameters. If you want to do that, you have to use these models. We really tried the opposite approach and reduce the number of parameters as much as possible. Another potential or another feature of potential interest for a certain class of a certain class of polymers, the so-called semiflexible polymers, is if you take that model that I just described and add a bending restraint. So we have a bending penalty. Of course, you can choose some non-zero value here for non-pi value for the reference angle theta, and whenever you rotate out of that angle, then you have to pay a penalty. Again, another energy scale, another reference scale in this term. In this sense here, in this context here, it's a reference angle, so the optimum bond angle. And then another class of polymers that I would like to target today here is helical polymers. So we use the standard model, let's call it like this, plus or not plus the bending restraint. I will discuss that in a second. But definitely adding another energetic component, another energetic potential in some effective form that mimics finally the formation of hydrogen bonds in a very simple way. So we introduce some torsion potential that allows us finally to simulate helical polymers according to a model introduced by or used by Dennis Rappaport also several years ago. So nothing of this here is really new. Many people have worked with these models for decades. But the problem is back then computers were available to some extent, but not with the power that we have nowadays, and many modern questions are asked nowadays about these systems, and we have now the computers and new simulation methodologies, so we can look into this much more thoroughly than it was possible beforehand. Okay, I will not going to talk about algorithms at all in this talk. We have used some specialized algorithms, in particular for lattice simulations, for all simulations of models, of the type of models that I just showed you. We almost exclusively use parallel tempering. Here you just see a brief collection of methods that were developed within a certain period of time that was really kind of hot. I mean, this was when really a lot, I mean, kind of a breakthrough in algorithmic development was achieved, introducing or starting with replica exchange methods, multiple histogram reweighting methods that finally led to the introduction of parallel tempering, the kind of complementary version, simulated tempering, then multi-canonical sampling, which really marked kind of a end point of that development. And Wang-Landau method, of course, came a little bit later. We have heard so much about Wang-Landau, I don't say anything about it. Of course, there was development since then, but I think that was really the breakthrough period. But most of these methods introduce a new quantity, which is quite old actually, but was never measurable by means of mathematical tools. That's the density of states for a computer. That's the obvious quantity to measure. So that might actually bring up the question, maybe that's more fundamental in all statistical physics than we all the time before believed, because of course you always believe what you can treat, what you can deal with, and if a mathematical physicist cannot deal with the density of states, then it's not a relevant quantity. But from the computational physics point of view, statistical computational physics point of view, that seems to be really relevant. We can start basically deriving everything just on the basis of the density of states. But I don't go into this detail as well. As I said, I follow more the traditional approach. Just a few examples that I have discussed in the last meeting or last two meetings, so I don't go into any detail here anymore. Flexible polymers, that was what I call the standard model, basically, so some Fini interaction here, some non-bonded monomer interaction. What I want to just mention here is a flexible polymer typically out of kind of a random call or gas phase first forms some globular phase if you cool it down, which we can consider something similar to a liquid before it finally crystallizes into some certain structure, and under certain conditions you find beautiful highly compact structures like icosahedrons, which I call the best natural approximation to a sphere. That's why a large class of viruses forms icosahedral shapes, because that's the best discrete way of forming something that has a large, an optimal surface to volume ratio like a sphere. But of course, it's a discrete system, so it's not going to be a sphere at the end. Anyway, so this is what we discussed a long time ago. I don't want to go into this, but just remind you of very compact shapes, which are not necessarily showing up any sort of symmetries, only in very special cases. Then another example that I discussed back then was if you add the bending constraint or restraint to the standard model of flexible polymers, you end up with so-called semi-flexible polymers. For decades only, this area here in the temperature bending rigidity or bending stiffness diagram, only this area was really covered by the so-called warmlike chain model. You see there's nothing from a point of view of structure formation, there's nothing interesting happening at all. But nonetheless, of course, semi-flexible polymers have a rich variety of structural phases. So independence of this bending stiffness or bending energy scale, you can find either towards the flexible limit that I just mentioned, these kind of very compact, nicely ordered structures. If you get bending effects, so bending starts costing a lot of energy, then of course the system tries to avoid these bands in order to maximize the number of, maximize the number of contacts among the monomers. So that leads to these sort of rods, and of course the stiffer or the more energy it costs to crystallize the system, particularly including bends, the fewer bends you will find. So the rods become longer and thinner until you have really a crossover in a completely different regime. So for very stiff or relatively stiff chains, you find these toroidal loops or hairpin structures that we know from RNA and DNA structures. So this is a simple system, simple model. The simulation is everything else than trivial, but we end up with absolutely reasonable results here that have some connection, of course, to reality. So it starts making sense. By the way, this work was done in collaboration with Daniel Seaton, who is still very well known to many participants of this workshop, although he's doing other things now. He is at MIT in a prominent administrative position, managing a research program there. Stefan Schnabel was a former student of mine, postdoc of David Landau. David was also involved in that study, of course, because he was the advisor of Daniel at that time. Okay, so now let's really go into helical polymers, or helical proteins, just as a reminder that these systems really exist in nature. This is a real protein, or a real synthetic peptide. It's not a big thing at all, 73 amino acids, so that's of the order of maybe 700, 800 atoms. So comparatively small, but of course relatively large if you want to really treat that system precisely on a computer with all these constraints that I mentioned before. It is known from experiment that it folds into a 3-helix bundle. What does that mean? At high temperatures, in the denatured state of the system, it's basically random, just a random linear chain floating around in space. But if you decrease temperature, or as we did it here in a microcanonical sense, decrease the system energy as such. It undergoes a certain dramatic or significant change. It forms the structure, it forms indeed, I mean, we could reproduce that easily in a simulation with a semi-microscopic model actually, so that's not a coarse-grained model here. I mean, it's coarse-grained in some sense, but not as much as I have described it before. So consider this more microscopic approach here, and it folds really into this 3-helix bundle, and it works very nicely, but you see very dramatic change in the shape, so why not calling that a transition in the context of phase transitions? We see signals really similar to what you see if you, for example, analyze microcanonically by means of finite size scaling, for example, first order transitions. In some sense, in some context, you see these features here in the microcanonical inverse temperature curves as a function of energy. So the so-called backbending effect is a clear indication for a first order transition. The dashed line, if you follow it from this point to this point, this range here is the latent heat, so it's really kind of a first order transition. Why does that happen here? That happens because of a loss of translational entropy. So again, as always, as it is in all thermodynamic phase transitions, you have a competition between energy and entropy, and here a massive loss of entropy leads finally, going along with a reduction of energy, leads to this kind of transition here. Okay, again, this is also just more kind of a motivation. So let's go really now into this system that I described. So we have now the standard model, so the flexible polymer plus the bending restraint, that makes it a semi-flexible polymer, plus the torsional interaction makes that a helical polymer model. So this is here a sketch of such a helical thing, and we want to describe the structural transitions. We want to understand the structural phases. We want to know how they look like. So we have to introduce some sort of parameters. Let's just call them order parameters or structural order parameters. Since we have to calculate Lennard-Jones energies between all these pairs of particles anyway, we have cutoffs included, of course. I don't want to go into those details, but in principle, calculating the energy is necessary anyway, so why not just splitting the Lennard-Jones part, the non-bonded energy, into two parts, which is written here in both, or represented by these two equations here. So what does that mean? So let's consider this monomer here, this one here as an example, as a reference monomer. It's bonded to these nearest neighbors along the chain. Of course, it interacts via the bond potential, but it can never interact them with non-bond, according to a non-bonded potential. So that's why we exclude them in the summations here. And then we have two classes of monomers with respect to this reference monomer. So if I change from here, this reference point from here to here, then basically like a red window, you shift it along the chain. So what we have here are monomers in a relatively close vicinity along the chain with respect to this reference monomer. We call them the near monomers, or the near interaction. Of course, every of those red monomers can get close to this black one here. So we have actually non-bonded interaction that will contribute here in this first, to this first parameter. Then we have the blue ones, which are more distant, more far away from this reference point, can get into close touch, like in this example here with the reference monomer. We count the energetic contributions separately in this second parameter. You may ask why just, for example, here 5 and not 6. The definition is robust enough. You can play with these numbers. Just for the parameterization we used, we decided that 5 is a good number. It really doesn't matter much. Okay, so that's what you keep please in mind, because I will talk only about these Q1, Q2 parameters from now on. These are my two order parameters. So whenever I talk about a free energy landscape, I try to parameterize them with respect to these two parameters. So this is my order parameter vector that I consider containing complete information about all kinds of structures that the system can fold into. Okay, so we have that system, and we discuss now two cases, the model that I just described, including the bending penalty, and then we exclude the bending penalty just to see what the differences are. Because it apparently turns out there is something to it that we have included the bending restraint. So if you just look into, you start your paratempering simulation, decent number of temperature threads, let's say 32, run them for a while, just pick a few structures out of all those all billions that you create, and just look at them visually, look what they look like, and then for example, relatively quickly you identify these 7 different kind of structural phases. So you can easily find, of course, identify a single helix, a 2 helix bundle, a 3 helix bundle, 4 helix bundle. I should mention that the length of the chain is 40 monomers, so relatively short, but that was what was manageable at that time, and completely sufficient for what we were interested in. You find something that doesn't really have structure. It's very compact. Very rigid, so it's not liquid in a sense, so it does not contain sort of viscosity. Viscosity that would make it a liquid, so we call that an amorphous solid. Then we have a liquid phase with kind of local ordering, but not global. And of course, we have the random coils as the simplest phase. So what you can do now is just basically what I said. I mean, you pick all these structures and identify in the Q1, Q2 space where you find them. Of course, what you really do is to go through the entire multiplicative ensemble that paratempering produces, so some kind of sketch of a multi-canonical ensemble or multi-canonical distribution, parameterized with respect to these 2 parameters, and then just identify, like by creating a map, you just identify these regions in Q1, Q2 space where you find prominently these structures. And that's what we did. As I said, I don't really want to go into much detail. We can discuss it in person if you want. But what you see here are yellow area, for example. So yellow corresponds to this yellow here. So it's where the single helices dominate, and it's perfectly clear. Q2 has its largest value. I mean, largest in a sense of close to 0. That means this parameter is almost 0. This means these blue monomers do not contribute at all. So all we see is interaction with the nearest neighbors, if you like, along the chain. This is what makes that Q1 value so negative, and that means we clearly have local interaction dominating the entire structure, and that's what you have when you have a single helix. 2 helix bundle is a little bit different, of course. Then you have the local ordering in these helical segments, but the helices align with respect to each other, so you have non-bonded interaction between the monomers in these different helix segments. This makes the 2 helix bundle, and of course that applies also for the higher ordered or higher order bundled formations here. You have a relatively large section where you have some sort of a liquid phase. Here it's the trivial random coil phase, here the amorphous solid. The amorphous solid, of course, has a relatively small, let's put it like that, a relatively large Q1 value, because for the amorphous solid, you have hardly any local ordering or local interaction, but a lot of global interaction between these more distant monomers, and that's why you have a very negative Q2 value, but not so negative Q1 value. So that's basically the opposite in this kind of, if you mirror it, the opposite side of this phase diagram here, if you want, compared to the 1 helix case. This is with bending restraint. So just as a reminder, because that's really, really important here, we have the option, of course, in our simulation to set that value to a decent number, non-zero positive number, so a large energy scale if you want, and we can set it to 0. That would represent basically a flexible polymer with a torsion restraint. So does that make any, what is the effect of doing that? Well, you see that on the right-hand side. It's whatever, without talking about it, you notice that it looks completely different from what is on the left-hand side. So this is just kind of giving you some evidence, at least some qualitative evidence, that the parameterization in Q1, Q2 space makes perfect sense, because for the flexible polymer, that's what I just briefly mentioned earlier, you have really not such a great variety of phases at all, actually only these 3, and you have absolutely nothing that reminds you of a helix at all. So to distinguish helices, it makes perfect sense to introduce these parameters, and much more important, we need the bending restraint. So in other words, a flexible protein could never be functional, because in the proteins, as we typically observe, you find a lot of local helical structures, in particular helix bundle structures. Okay. Maybe to save some time, I skip the part here about talking about what these black lines here mean. Okay, let's skip that. I can reorganize, of course, my interpretation in some sense, not discussing the Q1, Q2 space anymore. Now that I know how to identify these structures and look into these free energy landscapes, for example, I can now really change the torsional energy scale, and I can change the temperature. We can do that in our simulations, of course, relatively easily, and plot something like a phase diagram. So in this epsilon tor T space, we find again the random coil structures here. We have transitions into a much more structured low energy region where we have the 1 helix bundle, 2 helix bundle, 3, 4 helix bundle amorphous solid and the liquid phase here. This only applies if we have a bending restraint. If there is no bending penalty at all, then there is basically nothing interesting happening at all. Yeah, okay, I should have said that, yes, the Lennard-Jones energy scale is our base energy, our global energy scale, and therefore all temperatures are measured. KBT is measured in units of the Lennard-Jones energy scale. Yeah, I should have said that, but of course, that's the standard thing you do typically. Anyway, so I just want to convince you, we see clear differences in these two cases, if you have a bending restraint, like here on the left-hand side, or if you don't have it. So, as I said, proteins in reality, it's difficult, as I said, to identify really the degrees of freedom, but effectively, they have to be treated like semiflexible polymers, which most people actually agree with. Flexible polymers, like, let's say, polyethylene would never fold into some prominent helical structures at all. And as I said before, semi-flexible polymers don't do it either as long as you don't have torsional interaction. So you see things somehow seem to make sense. So if you want to discuss stability, the stability of these helical structures, let's again fall back on our parameters, and just to make things a little bit simpler, we just introduce this kind of fraction of the distant contributions to the Lennard-Jones or non-bonded energy of these structures. So we do it this way, so we can measure that in our simulations as, at a given temperature, for example, and parameterize that with respect to the torsion energy scale. So what you see, if you have no torsion at all, of course, the amorphous solids are the most prominent structure in the system at low temperatures, but already a relatively small energy scale that allows torsional interaction leads to the formation of 3 and 4 helix structures, which then, if you increase that number here, drop very sharply, form that very, very stable plateau of 2 helix structures, which finally break or just recombine, basically, in a sense, and form a single helix. This is the other question, of course, is not only stability with respect to the torsion energy scale, because of course that doesn't, the system doesn't change that by itself, so it's really different polymers that you consider, so an entire class basically that is covered by these values here. Of course, we can also change the temperature, and then you can ask how stable are these helical structures if I change the temperature, if I heat the system up. But you see, of course, kind of a melting of these steps here. But the 1 helix case, of course, is still very strongly, prominently available here, even at relatively high temperatures. We can then discuss, you may say, that may all be specific for n equal 40, and there are some specific features, of course, for exactly that chain length, but in order to figure out what is specific and what is more generic, we, of course, studied also other chain lengths which are close by, just to see what is the trend if I make the chain shorter or make the chain longer. This is now for bending restrained helical polymers only. As I said, the other case didn't show any interesting features. So what we see here is the only interesting part here is the single helix phase, the 2 helix phase, and here the amorphous solid maybe, and how that changes if I increase the system size slightly. You see, the only effect that really happens is that the larger the system, the more or the higher order the structures that you start introducing. So the 3 helix structure starts showing up here. which becomes more prominent if you make the chain length longer. If you would make it longer and longer, you create 4 helices, 5 helices. But at some point, of course, doesn't really make sense anymore because realistic macromolecules don't only consist of helices. You have other secondary structures that start mattering as well. So one has to incorporate additional model features in order to capture these effects. But this was just to make sure. But again, I mean, just going to n to infinity doesn't really make any sense. So the thermodynamic limit is not of any interest here at all. We know what would happen, but that's not interesting. What is really interesting to see is the larger the system, the more structure the most compact phase has. And that's what I observed in everything I did in this polymer science. So it's not that the larger the system, the clearer the picture. It's actually the opposite. The solid phase, the crystal phase become more and more complicated the larger the system. I think that has been overlooked for many decades, because nobody, it's very hard to really carefully look into the solid phases, the crystal phases. Water, you know that how many crystal phases are currently known. It's a large number. It's very difficult to really intrude into the crystal phases and to identify these kind of local subphases here in these phase diagrams. All right. Let's get, let me jump over that here. That's adsorption. We can, of course, also investigate the stability of helical structures under interaction with a solid substrate. I don't think I have the time to really go into this. Just as a remark, there has been some speculation about that the interaction of biologically relevant molecules with some silicon-based substrate might have been favorable in the evolution of early life forms. So that's why we just got interested in investigating how helical structures behave near solid substrates. And we see indeed that particular certain types of flat helix bundles, like 2 helix bundles, for example, become more and more prominent, but that's basically due to entropic effects. Anyways, let's go into the final part of this talk, and we completely forget now about semiflexible polymers and forget about helical polymers. We fall really back to flexible polymers, use the simplest model that you can imagine. It's you have a cubic lattice, we have some substrate here, and so the only thing that matters are nearest neighbor, it's a linear chain, you cannot really see it here, but it's a linear chain. What only counts are nearest neighbor contacts, so whenever 2 monomers that are not bonded to each other come close on the lattice, are nearest neighbors on the lattice, then we start counting, or then they are counted. Same if monomers get close to the substrate and are nearest neighbors basically to this plane here, then we count them as well and call these contacts here n as the number of surface contacts. The other one is the number of monomer contacts. This figure here makes one of the authors of this paper particularly happy. We call it Galo because that's the mascot of Paolo's favorite soccer team in Belo Horizonte. I found it accidentally in the simulation, so it's not made up really. It just looked funny and looked a little bit like chicken. Anyway, what's more important, actually, that's totally, the structure itself looks funny and it explains a little bit what we are doing, but it's completely irrelevant in the context that I want to talk about because it's a desorbed structure and we are not really looking into this. I should mention, this is my model. I just count these contacts. As I say, I just assign a minus sign to these numbers of contacts, so we just count and say this is the energy of the system is smaller the more contacts of any type I find. And I have a parameter, a single parameter here in this game. This is this so-called, what we call reciprocal solvent quality parameter. So some parameter that tells me, or that allows me to distinguish the influence of monomer-monomer contacts compared to surface contacts. So the more compact the structure, so the more of those contacts you have, or the more you favor that part here, the less apparently the smaller the quality of the solvent, if you like. That's why it is reciprocal. So anyways, let's now look into just ordinary thermodynamic quantities so we can measure in our simulations the averages of these two, let's say, order parameters now. We just decompose the model, the energetic model again, like we did before. It seemed to work well previously, so why not doing it again? So we consider these parameters, the order parameters in the system. Again, a pair makes sense here. in this constellation. So we measure them, calculate the average, consider the fluctuation of the quantity, so derivative of this average with respect to temperature. Here in the first figure, it's the surface, fluctuation of the surface contacts, and the second figure, it's the fluctuation of the monomer-monomer contacts. We measure the kind of probability to find, basically probability landscape of these two quantities with respect to these two parameters that we have, this model parameter or solvent parameter, if you like, and the temperature again. And what you see certain features in these kinds of phase diagrams. The brighter the color, the more intense the signal. Red is basically 0 if you want. So we see some action here. We see some same action in the same area here in the lower diagram, but we see also some additional activity here. So what does that mean? Let's look into these averages themselves for the case of a relatively small S value, and let's call that the good solvent case. So we go from left to right here across possibly this line if there's anything. Of course, it's suggestive because I put it there already. So 0.3 here, so we cross here through that area as well in these two figures. You see a strong reaction in this, or strong change in the number of monomer-monomer contacts here at a certain temperature, but hardly any change of the number of surface contacts. If we look into the structures, we have this kind of phase AC1 here, which corresponds to monolayers, compact monolayers, basically film-like structures. And if only the number of monomer-monomer contacts changes dramatically, actually, or rapidly decreases, then apparently the structure dissolves. That's why it is a good solvent case. But it happens on the substrate. That means the number of surface contacts hardly changes. As you can see, it's a plateau here in this area. So not much happens here at all. We call that phase AE, adsorbed, expanded structure. So like what we see here is something like a inverse crystallization transition basically on the substrate, so in 2 dimensions if you want. Of course, we can play that game. I like that. Sorry. We can, of course, do the same thing for the case that we might consider a bad solvent or poor solvent case. So let's increase the value of S to 0.8. Let's cross the phase diagram here, and let's cross it here. And you see already we have a strong signal in this quantity, we have a strong signal in this quantity. So whereas the number of surface contacts rapidly decreases, the number of monomer-monomer contacts rapidly increases at exactly the same temperature. This is what we call interlocking order parameters. They perfectly correspond to each other. And that's due to finite size. Again, on the left-hand side, we have the same phase as before, so AC1. On the right-hand side, we have a different phase now. So here in this area, or in this phase region, we have layering effects. So as I said, the number of monomer-monomer contacts becomes larger. That means the structure becomes more and more compact. But since we have already the most compact structure on the substrate, it means it has to rise, basically, or kind of lift off the substrate, de-wet in some sense. So the surface, the coverage becomes smaller. That means the number of surface contacts correspondingly rapidly decreases. So that's why we get that signal here, and we end up with structures like this here as an example, for example. Okay, so we have understood that part. Now this is my most favorite figure all time. I have to say that. I call it the most difficult or most complex phase diagram ever discovered. And of course, there's nothing really about phases. I mean, I already told you what these structural phases are. So that's why I better call it microphase diagram. What does it show? Parameterization is the same as before. Temperature here on that x-axis, solvent parameter on the y-axis. What I did here, or what we did here, was to calculate the free energy in this parameter space that I've introduced as a function basically of these contact numbers. And for a given pair of parameters, parameter values S and T, I calculate or try to find the global free energy minimum. And then I change one of those parameters. Let's say, for example, S, I change it a little bit. So I go from this point here a little bit up to this point, calculate the free energy landscape again. I don't need to do any further simulation because all this has been obtained in a single simulation. So it's just reweighting. Everything is reweighting here. It's just nice. So if I find that actually this kind of corresponding pair of order parameters has not changed its values, then nothing happens at all. So I consider this kind of a stability criterion within that kind of microphase. Only if I change, make another change in that parameter, and all of a sudden, the values of these contact numbers that correspond to the minimum, the global minimum in the free energy landscape, change, then I put a red dot there. It's a discrete model, and I'm really working here. I mean, it's a discrete space. So yeah, in a sense, of course, it's all kind of discontinuous. So it's a little bit difficult to distinguish. So I would not momentarily really go and say, I mean, these microphase transition lines, whether they are first or second order. Although one can do that. One can do that because what you see here, and that's the purpose of this, in this adsorbed expanded phase, these were these extended structures on the surface. You see many of these little bubbles here. What does that mean? They are a rapid change, by a small change in temperature or this order parameter here, the solvent parameter here, the actual state of the system changes a little bit. The overall features are still the same, but quantitatively I have a dramatic change. So in other words, if you have a large number of these small bubbles in a phase, that means it's entropy dominated. Changes are happening rapidly, but the overall structure of the phase is unaffected. Whereas in the other two cases, we deal with very large bubbles. Everything is stable, locally stable. It really requires a dramatic change to switch from one of the microphases to another one. That's energy-based. So we have all these transitions here are rather energy-based. And you see the dramatic change, in particular along this transition line here between these two kinds of behaviors. So I just like that because for myself at least, I found that quite instructive. Marcia, I hoped that since David isn't here anymore, I don't get a question to the error bars. No, you are right. There are, in a sense, error bars, but these error bars would not be sufficiently large in these two directions to really destroy my interpretation. You might observe that you might lose one or the other of these microphases to the error bar. Of course, yeah, I should have put error bars there, but I didn't put that effort in. This was a slide that I did for myself it's the first time I presented, but it's relatively older actually. I just did that for myself, but I found it fitted into this context here, and that's why I show it to you nowadays. Okay, last point, very recent stuff here. And that's now really talking about scaling. Of course, you can do some scaling. When I talked about, I mean, we stick to this model here. We discuss exactly the same model, so nothing changes to this model. It's actually the same data in a sense. But now I do not restrict myself to this area here, which is somehow bounded here at this point. We actually extend that more into this direction. All this stuff here is adsorbed. All these phases are adsorbed phases, or the structures are primarily located on the substrate. Of course, there is a point where these structures, the polymer starts desorbing, getting away from the substrate, so we have some sort of adsorption-desorption transition at higher temperatures here somewhere, and that's exactly what I'm talking about now. And this is nice work done together with Joao Plascar, Paulo Martins. So let's discuss scaling properties of the adsorption transition. In principle, an old problem. We know that the number of surface contacts scales with a certain, or according to a certain scaling law, the number of monomers to power to this exponent phi here. Basically, some corrections to scaling. We have a scaling variable, basically the temperature deviation from the adsorption temperature, which also scales with a certain length dependence here, with an exponent 1 over delta, which reappears if we look into the fluctuations of one of those order parameters. I already introduced, the fluctuations of, or the logarithm of the fluctuations here of these surface contacts. So it reappears here. Again, this is at this point just an assumption that these scaling laws hold. So we have to test them. So the first thing, of course, is to look into this quantity here, because as we figure out these peak values, as we just locate the maxima of these quantities here, of this quantity, for the different for the different system sizes that we look into, and we figure out that these are already very close to the final adsorption temperature, so hardly change the peak location, hardly change, so we do not assume complex behavior here of these scaling functions, so we can consider them constant. If that works out perfectly at the end, we have to see when we look into the results, but it turns out it was reasonable to do this, which gives us immediate access to the exponent 1 over delta. And you see 1 over delta also appears here in the context of the temperature, so we can also introduce, of course, the finite adsorption temperature Tn, and related to the adsorption temperature and the thermodynamic limit with this scaling correction, if you want. So 1 over delta appears here. We already know 1 over delta from this previous analysis. Can look into the Binder cumulants of that average, or of that adsorption, or number of surface contacts. So this is plotted here. We just take the results for the smaller system. I should have said that we have data available for system sizes 16, 32, and so on, until 503. And we take the smallest, the Binder cumulant for the smallest chain here. This is the solid line here that looks like a real line, although of course it's not. And consider all the crossings with the curves for the larger systems. So these are the yellow dots here, so in Brazilian color, yellow and green. And then we translate that here into the T over N to the power of 1 over delta diagram. And you see we have already a nice sort of scaling. It's not perfect if we would consider a linear scaling law here in these variables. This is the red dashed curve, so we introduce, or we make use of these scaling corrections that we have here available. So we have another exponent which turns out to be universally 0.5. It's not really important here, but you see we can improve the scaling, the fit, by introducing these scaling corrections, and get this value, which is very close to what other people had done recently. I should also say this is just an example. This is has been done here for self-avoiding walks for the s equals 0 case. So we can do that, of course, for any s value, but here it's just shown as an example for this case. So now we have, and of course we can extrapolate that and get, as I said, the adsorption temperature. So we now have 1 over delta Ta, and that allows us to fall back here into the first equation to have access finally to phi. I didn't say that, but the 1 over delta curves are shown here for different s values, and you see if you can see that they change actually. We have the phi values here. They also change depending on the value of the solvent parameter. Just here as a side remark, we can pick the case again for the self-avoiding walks. Kurt Kremer can confirm that there has been for decades a discussion about the precise value of this phi. There have been massive theories making clear that this value has to be precisely, rigorously 1/2. Well, more recent estimates, including ours with real good confidence, seem to indicate that it's slightly smaller than 1/2 actually. Anyways, this is just, for us it's just a side result. We are really interested in getting these exponents, transition temperatures, as a function of the solvent parameter, so to learn something about the effect of the solvent, and that's the final diagram here, basically the adsorption temperature, solvent parameter, and here we have the transition line. It's for the case s equals 0, as I said, the self-avoiding walk, non-interacting self-avoiding walk adsorbing to the substrate. It has been known that this is a strict second-order phase transition, going back to Eisriegler, Kurt Kremer, and Kurt Binder, old paper, but absolutely influential. But here we see, of course, that these values change. The critical exponents and also transition temperature changes. Nonetheless, we still, because the scaling worked so well, we still, of course, have the assumption that the entire line is second order. But you see the exponents change for a certain positive value of that, positive values of that solvent parameter relatively rapidly, which might be an indication of the existence of some multi-critical points here in that region. Which makes perfect sense because we somehow, of course, have to connect the phase diagram that I just showed you to that phase diagram because it's the same parameterization. So when you continue this line, it will at some point, of course, reach that transition line here somewhere, and there must be some higher order critical point or something like that. All right, so that's basically everything I wanted to talk about. So the first thing we learned, or that we think we found out was that bending restraints stabilized secondary structures relevant. I mean, secondary structures meaning helical structures in this context here, which are relevant for biomacromolecules. I have not talked about the stabilization of helical structures by attractive substrates, but I have talked about the kind of effect of interlocking order parameters that help identify, understand structural transitions for polymer adsorption, and finally the scaling properties. Okay, so I thank Matt Williams, who was a former student of mine, who worked on all these helical polymers. Actually, really the order parameters were his ideas, so 99% of the credit goes to him. And a lot of credit for the other project, of course, more than 50% per person goes to Joao and Paulo, who we worked with, or who I worked with, particularly during the periods that I stayed in Brazil. So that's why I thank also the Brazilian founding Science Foundation here, and of course the American National Science Foundation. And yeah, if you want to look up some more details of other stuff, feel free to check our website. All right, thank you very much for your attention.